Good afternoon, everyone. My name is Pengbo Yan from Xiamen University, and today I'm excited to share our research on ZOS enhanced stability and endurance in mobile device with integrated zone namespace in universal flash storage. In the realm of mobile technology, universal flash storage or UFS is widely adopted due to its rapid data access capabilities. However, UFS uses a block interface that is inherently mismatched with the native structure of flash memory, leading to significant performance inefficiencies. To address these issues, we introduced Zone Namespace or ZS, a new storage paradigm under the NVMe protocol that reduces interface overhead by aligning storage management with the specific physical properties of flash memory. Our purpose solution ZOS integrates the ZS patch with the UFS protocol to mitigate interface mismatch and enhance the overall efficiency and performance of mobile storage systems. Let's delve into the core issues that plague traditional block interface storage solutions in mobile devices. This system suffers primarily from three critical challenges. First, the over-provisioning of space resources in significantly underutilized storage capacity, meaning that a large portion of the storage can be used by end user due to reversed space for system management. Second, the opaque garbage collection process inherent to this system often causes unpredictable high tail latency, severely affecting user experience during high-intensity operators. Third, this system exhibits low endurance due to high weight amplifications where the amount of physical weight is much higher than the logical weight requested by the system. Focusing on the Android mobile device storage system, the complexity of file system and partitioning is another layer of challenge. Android devices using different file systems and partition setup, which complicates the integration of new storage technologies like ZS. Moreover, the inherent mismatch of ZS with UVS, which is merely designed for NVMe, presents significant technical challenges. Additionally, the fixed capability of mobile device storage, which can't be expanded easily like PC storage, limits flexibility and future growth. Now let's talk about the advantages of zone namespace or ZS. ZS allows hosts to directly manage the flash translation layer or FTL, which leads to more transparent garbage collection process and reduce the need for over-provisioning by supporting append-only sequence weights. ZS effectively minimizes the generation of garbage that enhance the overall efficiency and endurance of the storage system. This transition to ZS makes a pivotal shift towards optimizing of mobile storage by aligning it more closely with the inherent characteristics of flash memory. Our motivation stems from a clear need to solve the block interface text problem of UFS, reduce the complexity of extended ZS interface, and especially optimize ZS for mobile device, which has not been adequately addressed by existing solutions. In mobile device, integrating ZS into UFS faces challenges due to complex OS partitions. Our ZFS solutions simplifies this with a dual data path design, enhance both performance and efficiency. At the file system layer, ZFS submit zone BIO interface manages state by aligning it with zone pathways based on partition address. In the block device layer, we configure device to zone mode to ease the shift from traditional to zone data manage, incorporating a host-side flash translation layer that improves data mapping and garbage collection. Finally, modifications in the device driver layer and firmware layer enable efficient handling of both traditional and zone requests, simplifying the extension of ZNS to UFS in mobile device. One of the cornerstone achievements of our ZOS project is successfully integrating this technology with the existing UFS protocol, specifically addressing the US interface. This integration posed a significant challenge due to the fundamental difference between the N1E-based ZNS and the UFS protocol, which is primarily designed for SCSI environments. To bridge this gap, our team expanded the host-side UFS drivers operational commands to facilitate zone management, which is a key command of ZNS, as illustrated in the figure. This adaptation involved introducing 6 new commands to the UFS application layer. These commands are pivotal for ensuring that ZS can function within the ecosystem, enabling the system to manage data storage more efficiently and with greater granularity. By extending this capability to the UFS protocol, the UFS not only improves capability but also leverages the strengths of zone storage to enhance overall device performance and endurance. A key advancement in our ZOS project is the optimization of the address transmission protocol. Traditionally, the protocol requires extensive DMA operators to handle lists of addresses, which added necessary complexity and latency. To streamline this process, we introduced a star address and address length mode in the UFS commands. This significant modification embeds a concise description of the address range directly into each command, dramatically reducing the need for multiple DMA operators. This efficient approach not only simplifies data management but also boosts the overall system performance by allowing quicker and more precise address computation. The result is a more responsive and efficient storage system optimized for high-speed demand of mobile devices. In ZFS, we utilize a host-based flash translation layer or FTL to optimize how storage is managed. This setup enabled flexible mapping of data, enhance the storage system efficiency. Through our design, logical block addresses from the file system are directly mapped to physical zone blocks, creating what we call a zone address. This mapping ensures that storage zones are evenly distributed across all logical unity numbers and planes, allowing parallel processing of multiple I/O requests, which boosts system responsiveness and throughput. We will simplify the traditional storage architecture by implementing a coarse-grained linear address mapping table for zone IDs. This approach reduces the DRAM need for address table, making our system more efficient by focusing on zone IDs rather than detail page and block table. In the UFS, our host-based garbage collection algorithm efficiently manages the data storage by adapting to different I/O conditions. During periods of intense I/O activity, if a deficient in a available block arises, the algorithm initiates garbage collection, employing a greedy mouse to target the zone with the minimal count of valuable pages for data eviction. The algorithm functions by categorizing zones into three distinct states based on data temperature, hot, warm, and cold. Initially, all zones are designated as hot. During GC of hot zones, valid data is relocated to warm zone, while for warm and cold zones, such relocations fall directed to cold zones. Post-zone reset, its state reverts to hot. It quicker I/O intervals. These garbage collection operations are periodically executed. A focus on zone view are pages predicting the worm pointer are invalid, thereby eliminating the necessity for data migration during GC. Let's look at some of the experimental results. We test ZOFS under various conditions using tools like FIO, LocusDB, and FieldBench. We utilize the QEMU emulator with FieldMU, which stands for Flash Emulator, to create a controlled environment that mimics the behavior of physical flash storage. For the implementation of ZOS, we base our system on the Android open source project AOSP 17, modifying it to integrate our ZOS architecture. This integration allowed us to directly compare the performance of ZOS with the baseline AOSP setup under identical conditions. By using AOSP as both the control and test platform, we ensure that any performance difference observed are thoroughly attributable to the enhancements brought by ZOS. In our innovation, ZOS demonstrated a significant reduction in tail latency compared to AOSP, specifically at the 99th percentile, where latency decreased by 36 to 41%, and the random weight latency by 28 to 31% at the 99th percentile. Reductions in weight and random weight latency were even more substantial, ranging from 68 to 78%. This reduces the frequency of disruptive garbage collection operations, thereby minimize latency scripts and enhance overall system responsiveness. Overall, ZOFS architecture's optimizations significantly mitigate tail latency, particularly from garbage collection operators, leading to a more reliable and fast storage system. Where the amplification factor is a critical metric for SSDs indicating how efficiently flash memory is used. In our study illustrated in the figure, we analyzed WF under different field system utilization rates for ZOFS compared to AOSP, incorporating various over-provisioning levels. Our results indicate that ZOFS consistently exhibits lower WF than AOSP at an NOP of 7%. As we increase AOSP's OP to 28% and 40%, its WF initially remains slightly higher than ZOS and only matches all fields below ZOS when the field system utilization exceeds 60%. However, such high OP levels in customer devices are impractical due to the significant reduction in available storage space. In contrast, ZFS leveraging ZAS technology achieves approximately 30% better efficiency in OP space. This allows us to meet customer storage need without sacrificing valuable space. App startup time is crucial for a good user experience on mobile device. To evaluate this, we measure how quickly popular applications like Firefox, Facebook, and YouTube load on ZOS compared to OSP. Our findings shown in the figure reveal that ZOS enhance app startup times by 4.6% over AOSP. This improvement is due to the ZOS's efficient I/O operations, better read-write process, and reduced read amplification. In essence, ZOS not only speeds up application response time but also improves the overall efficiency and responsiveness of mobile devices. In conclusion, by integrating ZS with the UVS framework, ZOS successfully tackles the challenge of operationing latency variations and limited storage endurance, and have long-plug mobile storage technology. The introduction of a dual data path design and a host-based FTL within ZOS has shown to be particularly effective in enhance storage efficiency and performance. So that's pretty much how about our work. Thank you for your time again.